Alright, this video deals with the third type of general reaction, single displacement reactions. Single displacement reactions are sometimes also called replacement reactions, and you'll see why as we get going here. But basically, one element is going to replace a similar element in a compound. These reactions usually occur when the compound is in an aqueous solution. In other words, when it's dissolved in water. The single displacement reactions can be expressed this way. A plus Bx yields Ax plus B. And this is what I was saying, an element will replace a similar element in a compound. A is a metal, B is a metal. A replaces B in the compound, and you end up with Ax plus B. So the A and the B just trade places here. So this would be a metal replacing a metal in a compound. Or you can have Y plus Bx, non-metal plus metal, non-metal compound gives By plus X. So again, the X and the Y just trade places here. Those are the non-metals. So a metal can replace a metal, a non-metal can replace a non-metal. You can never have a metal replacing a non-metal or a non-metal replacing a metal. They have to replace their like ones. And this includes things when you have, for example, as I mentioned earlier, the nitrate or the ammonium ion is considered a metallic ion. So you could have NH4 here, and that might be replaced by a more active metal. Okay, but metal replaces metal, non-metal replaces non-metal. That's extremely important. Don't forget that. Okay, and here you see that A and B are metals, X and Y are non-metals, AX, BX, and BY would be compounds. Now, there's a number of special cases that you need to be aware of. The first one is the displacement of a metal in a compound by another metal. And this is probably the most common type of displacement reaction you'll run into. We will deal with activities of these metals and nonmetals, for that matter, when we get into the third section. For now, aluminum is more active than lead, so aluminum will replace lead in a compound. Here you see we have aluminum plus would be lead 2 nitrate. The aluminum is more active, and so it will replace the lead. The lead comes out, and you would find lead being deposited usually in the bottom of the beaker, and aluminum nitrate will be in aqueous solution. Okay, and that's very typical of the type of reaction that you get in this situation. Hydrogen can also be displaced in water by a metal. Remember that hydrogen is up above group 1, and so in some ways it does act like a metal, and so it can be replaced by metals if they are more reactive than the hydrogen. All of the group 1 metals are more reactive than hydrogen, and so those metals will react very vigorously. As a matter of fact, it can be dangerous to actually see these for these reactions to occur. We generally use very, very small amounts with lithium and sodium in the laboratory. Beyond that, we don't even do it because it's too dangerous. And you'll see a video or a link to a video at the end here that will show that to you. But here you see sodium. When it's put in water, it produces sodium hydroxide, and hydrogen gas is given off. Now, hydrogen gas can be very explosive, and if this reaction will liberate a lot of heat, if it's enough to actually get a spark on, you can explode the hydrogen. That's why that one can be dangerous. Very, very small amounts of sodium. This can be done safely in the classroom, but you don't want to use too large a sample of sodium for that. Less active metals like iron will not react with liquid water, but they will react with steam to form a metal oxide in hydrogen gas. And that looks like this. You have iron plus H2O. This is steam. It's in the gaseous state. That produces the iron oxide, and again, hydrogen gas is liberated. Metals will react with acids, and the metal will replace the hydrogen in the acid. Again, this is more active metals. The metal has to be more active than hydrogen. Again, you'll see that in section 3. But you see an example here of here, magnesium. When that's placed in hydrochloric acid, you'll see bubbles of hydrogen gas being given off, and the magnesium chloride is left behind in the solution. Magnesium chloride is a salt, and so that type of reaction is common with many metals. Any metal that's more active than hydrogen, which is a lot of them, will do this. And it doesn't have to be just hydrochloric. It could be any of the main acids, hydrochloric, sulfuric, nitric. Most of them will react in a similar manner. Finally, displacement of halogens. You have to understand when you're well, first of all, a halogen can only replace another halogen. It cannot replace a metal. Fluorine is the most active halogen, and so it will replace any of the other halogens in compounds. So in any reaction, if you see fluorine plus and then some metal halide, the fluorine will definitely replace that other one. In group 17, each element can replace the ones below it, but not any of the ones above it. So chlorine will not replace fluorine, but fluorine will replace chlorine, okay, because chlorine is below fluorine. Here you see chlorine plus potassium bromide. Bromine is below chlorine in the periodic table, so chlorine will replace that. So these two are just going to trade places. Now you can't just trade the whole thing. You have to write the correct formula. Potassium chloride is KCl, and bromine, when it's all by itself, is Br2. So you can see the way this equation balances, and you got to be a little bit careful with that. You can't just take and write this whole thing in here. You do not get KCl2. You get 2KCl. Similarly, fluorine will replace sodium, the chlorine in sodium chloride, and produce sodium fluoride, and you get chlorine gas given off. Bromine plus potassium chloride. Bromine is below chlorine in the periodic table. No reaction. Bromine is not able to replace chlorine because it's beneath it in the periodic table. And that's the end of our discussion of single displacement reactions.